So good evening everyone. I am Anirban Maiti. So one of the TA for this NPTEL course entitled as a study guide in organic retrosynthesis problem solving approach. And the course instructor for this course is Professor Samik Nanda from IIT Kharagpur. So this is the week 11 tutorial for this course. So the first slide explain about syntones and synthetic equivalents. So basically, we have talked about this. Like whenever we will do the CC bond disconnections, let's say this is an organic molecule, and if we want to break this CC carbon carbon single bond, so we can break by like three ways. Like one is homolytic cleavage. Homolytic cleavage mean radical after cleaving you will get two radicals, like two radical carbons. And if you do heterolytic cleavage, that time you will get one positive charge and one negative charge. So depending upon the CC1 disconnection approach, we'll get different syntones. Now, if we do the heterolytic cleavage of CC bond of a given carbon carbon single bond, then we'll get so one donor syntone, another is acceptor syntone. So donor syntone mean this carbon. So this carbon in this molecule, this carbon is taking two electrons from this single bond. So this carbon will get the positive charge, right? So the carbocation that is known as acceptor syntone, and this carbanion is known as donor syntone. So now this donor syntone and acceptor syntone. So donor basically after this CC bond disconnection, we need to have some like after CC bond disconnection, we will get some donor syntone and acceptor syntone, right? Now, donor syntone and in forward synthesis, these donor syntones and acceptor syntones we can't directly use. So we need to have some synthetic equivalents. Those synthetic equivalents we can use in forward synthesis. So donor syntones and their corresponding synthetic equivalent. What will be the corresponding synthetic equivalent? So this we should have some idea. Okay. So I have written some examples of donor syntone and corresponding some synthetic equivalents also we have written. Acceptor syntone also we have written, and as well as synthetic equivalents also we have written. Okay. So now, so these all we need in forward synthesis and retrosynthetic analysis purpose. Okay. So now coming to our today's problem, first problem. So this is the molecule aromatic ring having two hydroxy group. One is, yeah, both is tertiary alcohol, and this aromatic ring is having on chlorine atom. Okay. So how we can think about a perfect retrosynthesis analysis? Okay. Now how we'll do? Just just is this thing how we can disconnect this molecule to get the fast electrons. Okay. So how we'll disconnect? Just think and write in your notebook, like which CC bond disconnection or which carbon oxygen bond disconnection we can do in first step. So let's see which CC1 disconnection will do. So we did this CC1 disconnection. Okay, so this two methyl carbon, this alcohol carbon, and this methyl, and this alcohol carbon, and this methyl bond disconnection we have done. So some functional group, we can say it is a Grignard addition to this ester. Okay, so two equivalent of methyl lithium or methyl magnesium iodide. So we can add, right. So two equivalent of this Grignard reagent we can add. So we'll get this molecule. So this starting sorry target molecule. So this is the target molecule. So this target molecule we could get from this ester, right? So what is the next? So this ester, from where we can get? So basically this ester we can get from this carbonyl compound. How we can get? Think how we can get. So that mean basically we need to add this ester functionality at this carbon, right? So this carbon we need to some add some ester functionality group or some synthetic equivalence corresponding to this ester to this carbon we need to add. Okay, so that we can get this ester finally. Okay, so how we'll do this conversion or this transformation in forward synthesis we can see. Okay, so any doubt in this slide for this retrosynthetic analysis? Yes. Or any other way to do the disconnection approach, you can write in comment section, or you can ask, you can tell me now. Okay, if you don't have any doubt, then we let's see what will be the forward synthesis and how we can convert the starting material to our desired target molecule. Okay, so in forward synthesis we will see this to this starting material to target molecule synthesis we will see. So forward synthesis first. Yeah, so this also we can get from chlorobenzene. Okay, so the simplest molecule will be the chlorobenzene, or the simplest, easiest starting material, right? So chlorobenzene, from chlorobenzene we can get this molecule. So now we'll start directly from this to this, then this to this, then this to this. Okay. Okay, now we'll see the forward synthesis. So from chlorobenzene we have started. So now from chlorobenzene to this we need to get. Okay, so chlorobenzene to this functional group we need to install in the chlorobenzene. Okay, so how we'll do this conversion? Okay, so what will be the reagents? Can anybody guess, or not guess, just can anybody tell the answer, correct answer? Or if you know the correct answer, write in comment section, and we will also see. Okay, what will be the correct reagents? So just tell me what will be the correct reagents to get this transformation. Okay. So basically, we need to add this carbonyl functionality, right? So we can do some Friedel cap acylation type of reaction. Okay, Friedel cap's alkylation, Friedel cap acylation reactions are there, right? So we can do some Friedel cap acylation reaction. Okay. So what will be the reagents then? So I have given the clue. Now you can think properly. What will be the exact reagent? Yeah. So this will be the corresponding reagent. Acetyl chloride, and we need to use some Lewis acid. So here we are using aluminum trichloride. So this is the Lewis acid and acetyl chloride. So this Lewis acid will coordinate with this oxygen, and it will, so basically electrophilic substitution reaction will happen. Right, right. So now, what will be the next? So next is we need to get this molecule. Okay. So how we can get this molecule from this? So what will be the reagents? So this is pretty easy. So you can tell easily what will be the reagent for this. So what is happening here? We are converting ketone to alcohol, and also this carbonyl carbon is having one cyanide group, right? So I have, so basically cyanide addition into ketone. Okay, so almost you got the hint. So what will be the reagent? So the reagent should be some cyanide source, right? And that should be ionic, so like potassium cyanide or sodium cyanide. Better to use sodium cyanide because potassium cyanide is more ionic, so it will dangerous to our health. Okay. So now the next is, so we need to treat this molecule with H2SO4. So what we will get? So in H2SO4, what will happen? In H2SO4, what will happen to this molecule? Okay. So H2SO4 is acidic, so cyanide will get affect in presence of H2SO4. So what exactly will happen? Just tell me. So basically, hydrolysis, partial hydrolysis will happen, and it will form amide. Okay. So mechanism you can try in notebook. So this is very good mechanism to do this cyanide to amide. You can do in your notebook. Okay. So by that time we will see the what will be the next step. So next step is we are treating with sodium hydroxide. Okay, very interesting. So what will happen if we treat this molecule with sodium hydroxide? Okay, aqueous sodium hydroxide. What you will get the product? Okay, which product you will get, or what type of transformation will happen? Just tell. So you will get this product. Okay. So amide to acid you will get. Okay. So basically cyanide hydrolysis is happening. This cyanide to ester acid, carboxylic acid, this hydrolysis is happening via two-step acid base workup. Okay, you will get this acid. Okay. So now next is methanolysis. So what product you will get? So this is pretty easy. You can write down the answer. Okay. So what will be the next product? So next product is the esterification. Okay. So you'll get this carboxylic acid to methyl ester. Now we need to get here at this carbon we need to get two methyl and one alcohol. Basically tertiary alcohol we need to get along with two methyl. So what reaction we can do? So what reaction we'll do? So basically we need to treat this molecule ester with two equivalent of methyl magnesium iodide or methyl lithium. Methyl magnesium iodide or methyl lithium both will work, and we will get addition of this methyl group to ester. Okay, and you will get this product. Okay, so first this ketone will form. So first, after addition of one ester, sorry, one Grignard reagent, we will get one carbonyl group. So I'll draw the intermediate. So first we will get this product after addition of one equivalent of methyl magnesium iodide. Then in second equivalent addition, it will give this alcohol. So ketone. So one equivalent of another equivalent of this methyl Grignard will add to this carbonyl group, and you will get this addition of two Grignard reagents ultimately. Okay, and you will end up with this two alcohol. Okay, diol. Got it? Or do you have any doubt? Or if you have any doubt, you can write in comment box. Okay, now we'll see the next problem. So for this molecule, so if you see this molecule, it is having this aromatic side, but this side that is connected to this alpha beta unsaturated carbonyl compound, and it is having this tertiary alcohol along with this cyclohexane. Okay, so what will be the good one to like good CC1 disconnection? Just think and write in your notebook. Then I'll show you. Okay. Okay, so we'll see. So basically, we are doing this CC1 disconnection. That is obvious because this will leads to the formation of this alpha beta unsaturated carbonyl compound. That means we can plan some allol type of reactions to get this molecule. So allol disconnection, like this disconnection, we can think by allol reaction. Okay, so basically that will lead to this carbonyl compound and this aromatic aldehyde, right? So this is pretty easy. Now, what will be the next carbon-carbon disconnection? So this benzaldehyde, so this is the benzaldehyde. So this is commercially available. So no need to think about further disconnection for this molecule, but we have to think about this molecule to disconnect. Okay. So what will be the disconnection? Proper disconnection. Okay. So what will be the disconnection approach? So this molecule. So we can think about this carbon-carbon bond disconnection. Okay, this carbon-carbon bond disconnection, and that will leads to this cyclohexanone and uh, this carbanion. Okay, so this and what will be the corresponding synthetic equivalent for this anion carbanion? So this will be the corresponding synthetic equivalent or some reagent derived like reagent synthetic equivalent or the reagents that will leads to this that will give this in situ this synthetic equivalent. Okay, so now, so we'll start from this methyl vinyl ether, and we'll see the next step will be the addition of tertiary butyl lithium. So that is the strong base. Okay, so basically we are having this methyl vinyl ether and we are adding tertiary butyl lithium. So this is a strong base having pK around 51. Okay, so tertiary of pK is 53. So the pK value of tertiary butyl lithium is 53. Okay, so that shows it is a strong base. So what will happen? So it will abstract proton. Okay, or some lithium halogen exchange will happen. Okay, so just what will be the next product? Just think and write down in your notebook or tell me the answer. What will happen in this step? So tertiary beta lithium is a strong base. So what product we will get? So basically, it will take proton. Okay, which proton? Already I have shown the proton, the hydrogen. That corresponding hydrogen it will abstract and it will give this vinyl anion. Okay, that means this will be the OR and this C minus and Li plus. So what will be the counter cation Li plus? Okay, so we'll get this. That means it will give this product. Okay, so basically lithium halogen exchange is happening we can say, sorry, not lithium halogen exchange. So basically lithiation is happening. Okay, so after taking proton, so now we need to add this vinyl lithium to the cyclohexanone. Okay, so what will be the product? Write down the product. A very easy reaction. Just 1 2 addition will happen, and you can write down the 1 2 addition product. Okay, so you'll get this product, right? Pretty simple. Basically, how we are getting this? Now just tell me. So we are adding this product. We are adding this reagent. Now we are having this ketone at this side. Okay, how this is happening? Can you draw? So so basically, after addition of this reagent, what we'll get exactly? This alcohol will get along with this addition of this, right? Now, what is this? This is basically enol ether. Okay, so uh, this is basically enol and ether. So methyl ether, enol methyl ether. Okay, so hydrolysis will take place in H3O plus. If you treat this with H3O plus, hydrolysis will take place and you will get enol, and enol will tautomerize to give this ketone, right? Now you got it. Yes. So the next, what will be the next step? So I have written the reagents and see, and what will happen is just tell me what will be the next step. Just tell me. So this is pretty simple. We have benzaldehyde, sodium methoxide, and solvent is methanol. So base, sodium methoxide is base. Benzaldehyde also we are using. So what will happen? So allele reaction will happen. Okay. So yeah, we will generate this enolate from this carbonyl compound. Then that enolate will add to this benzaldehyde, and it will give corresponding aldol product. Okay. So write down the product. Okay. So this will be the product. So first we will get beta hydroxy alcohol, sorry, beta hydroxy ketone, and then elimination will take place. Dehydration will take place, and it will give the resulted enone. Okay. So then it will give the resulted alpha beta unsaturated ketone. Okay. So any doubt in this slide? Okay, then we'll move to the next problem. So this is the molecule having this alpha hydroxy ketone. Okay. So last in this slide we are having okay. So in aldol reaction, what we'll get? So we'll get this basically if we are denoting this as a R. This is AR. So in aldol reaction, basically we'll get first this beta hydroxy ketone, right? So this we will get in aldol reaction. So beta hydroxy ketone. This is alpha. And this is beta carbon. So we'll get beta hydroxy ketone in aldol reaction. So now, if you see this molecule, it is alpha hydroxy ketone. Okay, alpha hydroxy ketone. So we can't get this molecule from aldol reaction. Now here also we have given some limitation that this R should not have any ionizable protons. Okay, and both are symmetrical and it's aromatic. So symmetrical are both are the same, and it should not have also any ionizable proton. And basically, if it is aromatic, then how we can synthesize this molecule? Okay, how we can synthesize this thing and write or comment on chat box. Okay, no problem. So basically we can think about if R is aromatic, no inalienable proton, and if it is alpha hydroxy ketone, then we can get this molecule via benzoin condensation. Okay, so if we should have this electrophilic, this aldehyde, and this nucleophilic aldehyde. Okay, so this will get in forward direction the benzene condensation product. Okay, I guess all of you know or heard about this benzene condensation, right? So then we'll see the forward synthesis. Okay, how it's happening. So basically we'll start from this benzaldehyde, where this phenyl is aromatic ring, no ionizable proton it has. So first we'll treat with sodium cyanide, and that too we'll use as catalytic amount. Okay, and ethanol is the solvent. So what will be the product? Write down the product name. So we'll get this alpha hydroxy ketone compound. Okay, after this reaction. So what will be the mechanism? Can you write down the mechanism? So first, obviously, cyanide addition will take place into benzaldehyde, and then another molecule of benzaldehyde will add to the carbon. Okay, of benzaldehyde carbon. So how this reaction is taking place? What will be the mechanism? Just write down the mechanism. So this cyanide addition will take place. Then what product we will get? So basically, we'll get this product. Okay. Now this molecule is in equilibrium with this form. Okay. How it is? So basically, if it is it is having this proton, right? So it will take abstract this proton, and it will generate this carbon anion. Okay, and this anion carbon anion will be in resonance form with this. Okay. So now what will be the next step? Okay, you are having another molecule of benzaldehyde. Now that will act as the electrophile. Okay, now I have given the clue, and you can, I guess, you can write down the next step. Okay, and the product or its product also. Okay, let's see. So basically we will have this product. Okay, so now this carbon here, this carbon, so this will fall back, and this carbon will act as a electrophile. Okay, sorry, nucleophile, and it will add to this electrophile. Okay, and it will give this product, right? So now what will happen, this OH, it is having this alcohol and this O minus, so this O minus will abstract this proton. Now it will generate this O minus and this alcohol. Okay, so now what will happen, this O minus will fall back and cyanide will leave, okay, as a Cn minus, and we'll get this product. Okay, so this is the mechanism, pretty easy, BSc level. And this so this is basically benzene condensation. Got it? Any problem or any doubt? Okay, then we'll see the next problem. So this is the molecule having these two amino group. One is aliphatic, another is aromatic. Okay. So what will be the fast disconnection approach? So basically we can get this molecule from these two nitro group. Okay. So nitro derivative. So now this molecule we could get from this compound. Okay. Right. Na. So via this SN2 reaction, okay, between this CC1 disconnection approach. So in forward synthesis, what will happen? So we are treating this as nitroisopropyl group with sodium ethoxide, that is a base, and this paranitro bromobenzene, benzyl bromide, that is as a electrophile. Okay, so what will be the product? Write down the product. Basically, simply this is abstract proton. So this is the acidic proton. So sodium ethoxide will abstract this proton, right? And it will generate this carbon and alpha to the nitro. Now this will act as a nucleophile, and electrophile is this 4 nitro paranitrobenzyl bromide. So it will, the session 2 will take place, okay, and you'll get this product. Now what is the next step? Next step is the simply reduction of nitro group. So reduction of nitro group. So what product we will get? Okay, just right. So basically reduction of nitro that will leads to this amine. Okay, one is aromatic, another is aliphatic. So reduction is we are doing via this by using this H2 hydrogen and renin nickel as a catalyst. Okay, so this is the forward synthesis. Any doubt in this slide? Okay, then next problem we'll see. So again another compound we are having. So this is also having this nitro group, sorry amine group, and now it is aliphatic amine. So now what we can think? Okay, so again, so this left hand side part that we can having this amine, but yeah, this side part we can think about this alpha beta unsaturated nitro group. Okay, so this we can do via hydrogenation condition, right? So if we do hydrogenation of this molecule, we'll get this. Now how we'll get this? So basically, so this is alpha beta unsaturated nitro compound. So again, this disconnection, this CC1 disconnection, double one disconnection, we are doing, and that will leads to some allele type of substrates. Okay, so you can think, you can easily write down the next molecules. So basically, we'll get this aldehyde and nitromethane. Okay, so basically, base will abstract proton from here, and allele reaction will take place, and it will give this alpha beta unsaturated nitro compound. Right now, this we how we could get. So this molecule in turns we could get from cyanide again through reduction. Okay, through reduction of cyanide, we'll get CH2 NH2. Easy. Now, so this molecule how we could get. So basically, if we do this CC1 disconnection, and we can do this Michael addition. Okay, Michael addition first, this carbanion generation, and then this can add to this acrylonitrile via 1,4 addition fashion, and it will give to your uh, 1,4 addition product. Okay, basically it will give this compound, right? So any doubt in this retrosynthetic analysis, you can ask in comment section as well. Okay, so the forward synthesis we'll see. Forward synthesis, so we'll start from these two molecules. And we are treating with sodium hydroxide, so that is base. So base will abstract this acidic proton, right? It will abstract this acidic proton, and then 1 pore addition will take place. Okay, carbonyl will generate here, and then 1 pore addition will take place. Basically, we'll get this product. Now, if you see triethylamine and nitromethane. Okay, so nitromethane, so it is also having acidic proton in this methyl. So nitromethane, so triethylamine will take proton from that nitromethane, and it will add to this aldehyde. So basically, aldol reaction will take place. First beta hydroxy is nitro derivative. This compound is forming. Now P2O5. P2O5 is dehydrating agent. Okay, phosphorus pentoxide. So it is a dehydrating agent. So what will happen? It will abstract water. Okay, from your molecule. So dehydrating agent in treatment with dehydrating agent, it will give you this corresponding alpha beta unsaturated product. Basically, elimination or dehydration is taking place, and we are getting this product. Now, one mistake also we did, that is the cyanide to amine we have written here. So basically, after first step, second step is hydrogenation. Okay, hydrogenation. If we do that time only, we will get cyanide to CH2 NH2, right? Pretty simple. Now, okay. So after getting this molecule, alpha beta unsaturated nitro. So if we treat with this hydrogen in Rhine nickel, so what will happen? So reduction will take place. So first this double bond reduction will happen. Also, this nitro group will reduce. Okay. So nitro group will reduce to give this amine. Okay. So now what will happen? You will get this product. Okay, so diamino compound. So this is our compound. We got this compound, right?